Welcome back. In this video, I'm going to show how to prove injectivity and surjectivity of functions. Let's recall the definition of injectivity. F from A to B is injective. That means that if you have two distinct members of A, then it cannot be mapped to the same value, right? Another way of calling injectivity is one-to-one function, right? So you can prove directly for injectivity. Sometimes it works, but it is actually easier to prove its contrapositive. So sometimes to prove injectivity is actually easier to show that for all x1, x2 in A, instead of showing this, you show that if fx1 is equal to fx2, then x1 is equal to x2. Yeah, the contrapositive of that implication. All right, so let's demonstrate this with an example. Show that this function from R to R given by fx equals to x plus 1 is injective. So we're going to use the contrapositive, okay? So I'm just use xy actually, it's a bit easier. Xy be in R, right? And we're gonna assume that fx is equal to fy. We want to show that x is equal to y. All right, assume that fx is equal to fy. We know exactly what they are, so we have 2x plus 1 is equal to 2y plus 1, right? And so 2x is equal to 2y, and finally x is equal to y, and we're done. So yeah, again, in most cases, the easiest way to show injectivity is to show the contrapositive of this implication, yeah? That for all x1, x2 in A, if fx1 equals fx2, then x1 equals x2. Okay, at this point, I would like to pause a moment and rather than going straight to surjectivity, word of advice, you can see now I'm started to combining all the proof techniques from before, right? I first understand the definition, and then this statement with quantifiers and so on and so forth, and now I'm using a indirect method of proving an implication. So the more you practice with proving different things, the more you have tools in your proof toolbox, if you will, right? And the better you are at proving things. Okay, so start from the previous videos and try to do some more exercises and take baby steps, right? Start with the simple one, try the one that's more complex, and so on and so on. And after many times practicing, you will get better. Now let's take a look at this example. We're going to show that this function is not injective. Okay, f is fx equals x squared. Show that this is not injective. Okay, so let's write down again the definition of injectivity. F is injective if what? If for all, have to have quantifiers first, for all x and y in R, if x not equal to y, then fx is not equal to fy. Okay, we are going to negate this statement. Okay, so what is the negation of this statement? The negation of this statement, we want to show not injective, so we look at the negation. The negation is, remember, for all becomes there exists xy in R such that this implication, now you want to negate it, right? Negation of an implication, P implies Q, is P and not Q. Okay, there exists xy in R such that P and not Q, such that x is not equal to y, but we can use n here, and fx is equal to fy. Okay, so that's what we want to show, right? We want to show that there exists xy in R such that x is not equal to y, but fx is equal to fy. Can you find two distinct x and y in which they are mapped by this function to the same value? In other words, their square is the same. Many choices. I'm going to choose x to be 1 and y to be -1. And we have that f of x is 1 and f of y is also 1, right? This is 1 squared equals 1 minus 1 squared equals 1. And we're done. There are two distinct points that are mapped to the same value. Okay. Now, how to prove that a function is surjective? Let's recall what it means by surjective. Function is surjective if for all y in B, the function goes from A to B, for all y in B in the codomain, there exists x in A with fx equal to y. Now let's show the same example as before, fx equals 2x plus 1, show that this function is surjective. Okay, so what do we want to show? We want to show a statement that has two quantifiers. For all y in B, there exists x in A with fx equal to A. All right, so let's start from the beginning. Let y in B be arbitrary. B in this case is R. Okay, and then we want to choose an x, right? There exists x, typically we choose or construct x. What we want is that fx is equal to y. Okay, but how are we getting this? This is when sometimes we need to work backwards, right? So I'm gonna have this portion of the slide to be my scratch paper, so to say. So what I want eventually is that I have a y that is equal to f of x, right? I don't know what x is. What is f of x? Is 2x plus 1, right? Oh, wait, if I can solve this for y, right? I can make 2x equals y minus 1, and x finally is y minus 1 over 2. So I know if I move backwards, right? If I start with x equals y minus 1 over 2, I will get that and get that, which means that y is equal to f of x. So this is my appropriate choice of x, right? So I'm going to choose x to be y minus 1 over 2. Okay, let me pause here for now. When you are reading somebody else's proof, okay, typically you don't read this scrap paper, right? They don't show this one. They don't show the thinking section, right? They only show you the final proof. This is maybe a fault of mathematicians because we like to present nice proofs, right? So you don't actually see sometimes in proofs these kind of details when people work backwards and so on and so forth. So it is actually very important to do lots of these kind of exercises for you to get some of these tricks, like when you need to move backwards and so on and so forth. Okay, so now let me carry on with the proof. Choose x to be y minus 1 over 2, right? And then, so where are we now? We have chosen y arbitrarily. We have chosen a specific x. We need to show that f of x is equal to 2. All right, choose x to be this. Therefore, f of x, which is f of y minus 1 over 2, is 2 times y minus 1 over 2 plus 1, yeah, 2 times x plus 1, which is equal to y minus 1 plus 1, which is equal to y, which is what we want to prove, right? We want to prove that f of x is equal to y. And we're done. So typically, to show surjectivity, at some point, you need to move backwards. Now, let's take a look at this example. We want to show that f, function from R to R, defined by fx equal x squared, is not surjective. All right. So again, we need to negate the definition of surjectivity. So f is surjective if what? For all members in its codomain, in this case R, for all y in R, there exists x in R such that fx is equal to y. And we want to negate the statement, okay? So negation of for all becomes there exists y in R. Now there's there exists, and this is going to change to for all. And that statement, we need to replace it with its negation. Fx is not equal to y. Okay, so this is what we want to prove now. This statement. So now we want to choose y and show that for all x in R, fx is not equal to y. Right. So let's see what we want now. We want to find a real number such that no x whose square is equal to y. That's essentially what it's saying, right? So a square number cannot be equal to a negative number, right? So any negative number will work as your choice of y. All right, so pick your favorite. Let's choose y to be -1, right? And let x be in R. Okay, since x squared is greater or equal to 0 for all x, we conclude that fx cannot be equal to a negative number. Okay, and we're done. Okay, very quickly, how to prove that a function is bijective. Remember what is bijective? It means that the function is injective and surjective. So you need to prove both. We already did it earlier. Our example that f is given by 2x plus 1, this is injective and surjective. Therefore, this is a bijection or a bijective function. Okay, so I'm not going to write down the proof. And I'm going to end here, and we will have one more video where I'm going to talk about other methods of proof that you may come across in the future. Okay, see you then.